Now, I'm going to give now a funny geometrical interpretation of the uncertainty. Maybe you will find it illuminating. In some way, it's turning into pictures all these calculations we've done. I think it actually adds value to it, and I don't think it's very well known. Or, you know, it's kind of funny because it might not be very well known, but maybe people don't find it that suggestive. But I kind of find it suggestive. So here is what I want to say. Geometrically, you have this vector space and you have a vector psi. Then you come along and you act with the operator A. Now, the fact that this thing is not an eigenstate means that after you act with A, you don't keep in the same direction. You go in different directions. So here is A psi. So what can we say here? Well, actually, here is this thing. Think of this vector space spanned by psi. Let's call it U psi. So it's that line there. You can project this in here orthogonally. Here is the first claim. The vector that you get up to here, this vector is nothing else but expectation value of A times psi. And that makes sense because a number times psi, but precisely the orthogonal projection is this. And here you get an orthogonal vector that we'll call it psi perp. And the funny thing about this psi perp is that its length is precisely the uncertainty. So all this, you could prove, I'm going to do it. I'm going to show you all these things are true. But it gives you a bit of an insight. You have a vector. A moves you out. What is the uncertainty is this vertical projection. Vertical thing is the uncertainty. If you down there, you get nothing. So how do we prove that? Well, let's construct a projector down to the space U psi, which is just psi, psi. This is a projector, just like any E1. E1 is a projection into the direction of 1. Well, you know, take your first basis vector to be psi, and that's a projection to the psi. So let's see what it's a projection to psi. So now let's see what it gives you when it acts on A psi. This projector acting on A psi is equal to psi, psi, A psi. And again, the usefulness of bracket notation is kind of nice here. So what is this? The expectation value of A. So indeed, psi, expectation value of A, is what you get when you project this down. So then the rest is sort of simple. If you take psi and subtract from psi, well, I'll subtract from psi psi times expectation value of A. You can, I'm sorry, I was saying it wrong. If you take the original vector, A psi, and subtract from it what we took out, which is psi times the expectation value of A, the projected thing, this is some vector. But the main thing is that this vector is orthogonal to psi. Why? If you take a psi on the left, this is orthogonal to psi. And how do you see it? Put a psi from the left. And what do you get here? Psi, A psi, which is expectation value of A. Psi, psi, which is 1. And expectation value of A is 0. So this is a vector psi perp. And this is, of course, A minus expectation value of A acting on the state psi. Well, precisely the norm of psi perp is the norm of this, but that's what we define to be the uncertainty. So, indeed, the norm of psi perp is delta A of psi. So our ideas of projectors and orthogonal projectors allow you to understand better what is the uncertainty, more pictorially. You have a pictures of vectors and orthogonal projections, and you want to make the uncertainty 0, you have to push the A psi into psi, you have to be an eigenstate, and